Morning, afternoon, or evening, everyone. Welcome to the From Ocean to Cloud Enabling Workflows and Data Utilization Earth Data webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started. I will begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, please enter those into the Q&A panel rather than the chat, and you'll find that located on the right side of your screen. Today's webinar is being recorded. The recording will be posted both to the NASA Earth Data website as well as to our NASA Earth Data YouTube channel within a few days of completion. Once completed, I will send an email to all registrants with the recording links and also a link to the presentation slide deck used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A session an additional 15 minutes from end time, but we will have a hard cutoff of 3:15 p.m. During today's webinar, we will have 3 speakers. Our first speaker is Julie Sanchez. Julie is a postdoctoral fellow with the Ocean Circulation and Air-Sea Interaction Group at NASA's Jet Propulsion Laboratory. She will begin today's webinar with an introduction to PO.DAAC and the core elements that will be covered within today's presentation. From there, she will transition to a use case that combines both soil moisture active-passive mission, or SMAP, and integrated multi-satellite retrievals for GPM, or iMerge data to investigate land-ocean connections during the winter California rain events. From there, we will transition to our second speaker for this afternoon, Victoria McDonald. Victoria is a data engineer at NASA's PO.DAAC, and she will provide a tutorial that shows you how to scale your scientific analysis using AWS Lambda for deploying cloud services for science workflows in the cloud. After she's finished with her tutorial, she will toss it over to our third and final speaker for this afternoon's event, Nikki Tibaldi. Nikki is a cloud adoption engineer at NASA PO.DAAC, and during her presentation, she will provide a case study of moving an advanced data generation workflow to the cloud. Once our speakers have finished with their webinar presentations, we will then move to our optional final set of polling questions. With that, it is my pleasure to introduce today's first speaker, Julie Sanchez. Julie, so at this point, I'm going to stop sharing my screen and toss the presenter role over to you.
Great, thank you. I'm going to share my screen. Okay, can you see that?
I can, that looks great.
Thank you. Okay, hi everyone, I'm Julie Sanchez. I'm a postdoc at the Jet Propulsion Laboratory, where I've been working with Victoria McDonald and Nikki Tibaldi at the Physical Oceanography Distributed Active Archive Center, also known as PO.DAAC. So PO.DAAC is one of 12 NASA data centers distributed across the country. PO.DAAC is in charge with making NASA mission data available and accessible for people to use for science. And at PO.DAAC, we mostly focus on oceanography data sets that measures things like sea surface temperature, ocean winds, and currents. We recently moved all of our data from on-premise servers into the cloud, and so cloud computing and Amazon Web Services opens up a lot of new capabilities. And part of what we want to do in this webinar is introduce users to the landscape of AWS services that are available. By moving some of our own processes and workflows at PO.DAAC to the cloud, we started exploring how some of these different services can be used for different types of analysis. So today we're going to take you through 3 different examples. The first is a science case study aimed at more novice cloud users, and we'll demonstrate using multiple data sets to explore the land-ocean connections during the California rain events in the wintertime. Next, my colleague Victoria will showcase a new tutorial that we've developed that demonstrates how to use AWS Lambda to scale a science workflow in the cloud. And finally, Nikki will discuss a more advanced workflow where we moved one of our internal data generation workflows into the cloud and some of the advantages that has opened up and lessons learned in the process. So I mentioned earlier, I'll talk about using PO.DAAC data to investigate the land-ocean connections during the winter California rain events. I'd also like to mention Edward Armstrong, who collaborated on this project with me. To start with a little bit of a background, atmospheric rivers are long, narrow bands of moisture in the atmosphere, which shows to the image on the right. 12 of these hit California from December 2022 to April 2023. For example, Honeydew, California, which is in Humboldt County in Northern California, received around 47 inches of rain. And just to add some further context, the annual average rainfall in California is about 22 inches. So these events caused major floods, loss of power, and closed many roads, but it also resupplied California reservoirs. The California map on the left is from August 9th, 2022. You notice the darker shades of red, which mean that there are exceptional drought or extreme drought in these areas. The California map on the right is from August 8th of this year, and it shows some areas in the northern and eastern parts of California as abnormally dry to moderately dry. So you notice that this is a completely different drought map from last year's. So the increased freshwater into the ocean from rivers, creeks, and streams can affect the ocean currents, stratification, sea level rise, and salinity. So salinity is estimated by measuring the electrical conductivity of water. So the more salt there is in the ocean, the higher the conductivity. Salinity is expressed in practical salinity units, PSU. The map that I have on here is the mean sea surface salinity from the Soil Moisture Active Passive, or the SMAP satellite. So you'll notice, for example, the North Pacific is colored in green and blue, which means it's lower in salinity than the Atlantic Ocean, which is colored in red, showing a higher salinity. So these events provided us with opportunities to observe the land-ocean connection. So what we really wanted to understand if there was any relationship between river runoff and ocean surface salinity in the coastal regions off of California. And if so, how can we monitor them using satellite data? I used two data sets, which can be found on the Earth Data Search. The first one I used is the Sea Surface Salinity data set from the SMAP satellite. It is a passive microwave instrument built and managed by JPL. It provides 8-day snapshots of sea surface salinity at a global scale with about a 60-kilometer resolution. A long-term mean is removed, so what is presented in the sea surface salinity anomaly analysis that I'll presenting the next few slides is the difference to the long-term mean. The second data set I use is the precipitation from integrated multi-satellite retrievers, IMERG for global precipitation measurement data set. It is a multi-satellite fusion product using passive microwave data, and it provides estimates of global precipitation at daily intervals at about 10 kilometers resolution. So I use the PO.DAAC data downloader, which is a Python-based tool for bulk and one-off or non-often downloading of data from the PO.DAAC archive. It was able to download months of data that I needed for the analysis fairly quickly. Okay, I'm going to play this animation. So what we're looking at is the sea surface salinity over the Pacific Ocean and precipitation over land in the western United States from December 2022 to April 2023. The color scale on the left shows the salinity anomaly from the mean over the full time span. So the red colors show that it is saltier than the mean and blue is fresher than the mean. The color scale on the right is not an anomaly. It's just the precipitation every day in millimeters per day. And so as the animation continues and goes through, you'll notice a lead lag effect. As more precipitation occurs over land in a matter of days and even weeks, the ocean becomes fresher. So therefore, impacts of runoff from heavy land precipitation into the ocean should be monitored and further researched. So if you want to learn how we did this analysis, this tutorial is on the PO.DAAC Cookbook. The Cookbook is a resource where we have lots of tutorials and examples that demonstrate how to access PO.DAAC data. And with that, I will conclude and pass it on to Victoria.
Thanks, Julie.
Let me stop sharing my screen.
My name is Victoria. I'm a data engineer at PO.DAAC, and I'm going to introduce a tutorial that a number of us have been working together on that goes a couple steps deeper into using cloud computing capabilities. And we're centering this example on the AWS Lambda service. So just to bring this back to what Julie introduced, this is intended to help users understand a bit more of the landscape of different AWS services that are available and how to chain those together in different ways to do analysis of the cloud without having to download the data locally. So maybe you've played around with creating your own AWS account. Maybe you've gotten a Jupyter notebook running in the cloud and done some analysis, and now you're ready to branch out a little bit further and start using some of the other services that are available. That's sort of the level that we're aiming this tutorial at. So Lambda is what they call a serverless computing service, which means it will run a piece of code that you've configured, but you don't have to set up a whole physical or virtual machine to run it. You don't need to specify the optimal combination of CPU and memory and disk storage, and account for parallel processing when you scale up to analyzing maybe thousands of data files. Amazon handles all of that for you. Lambda is event-driven, so in this example, we're going to invoke the function manually in a Jupyter notebook, but you could also set it up to run automatically and be triggered by something else happening in your AWS environment. For example, if you moved a file into an S3 bucket, you could have a Lambda function automatically run and process that file when it gets uploaded without having to invoke that action yourself. There are a few limitations with the Lambda service to be aware of. It does have a 15-minute execution timeout, so you don't want to put all of your code for a long-running process into one Lambda function. You would probably want to re-architect that workflow to have shorter running tasks chained together with step functions. There are also storage and concurrent execution limitations that can be increased from the defaults, but they aren't unlimited. And so any output from the calculations that you want to save needs to be stored somewhere outside of the Lambda function. So in this example, we'll write the results out to an S3 bucket. You do need to allocate the memory that your function will need to process one file in advance. And then when the Lambda is running on many files, it knows how much memory to allocate for each one. And then finally, Lambda functions can't really talk to each other when they're running. So some types of science questions and statistics are a little bit more complicated to handle. This is something that we're working on for the next version of this workflow. But for this tutorial, we're going to use a calculation that can be done in isolation on one file. And then we'll aggregate the results at the end outside of the Lambda function to try to keep this workflow as simple as possible. So the calculation that we're going to use to demonstrate this is a global mean of sea surface temperature. This is one of the high-resolution oceanography datasets that we host at PO.DAAC. And each file in this dataset contains data for the global ocean for a single day. So if you wanted to see how ocean temperature is changing, maybe over the past year, you would need to open 365 files, one for each day. If you wanted to look at a longer period, the number of files is going to increase. The Lambda function is going to calculate the area-weighted global mean. So it's going to reduce each of these daily files down to just one number. We're going to start with how the end user is going to interact with this once it's set up and running. And as we walk through that, we'll bring in the various other components that are needed to support this workflow and have it run successfully. So the user that we have in mind might be doing their analysis in a Jupyter notebook. The first step of that notebook is going to be finding the files that you want to do your analysis on. So we're going to start with a query to find that list of files. And just note that we also call files granules, so you might see that term. And we need to know where those files live. So once we have that list, we're going to loop through them and invoke the Lambda function on each one. The Lambda is going to run in the background to process each file and create output files that hold the results. And then the final step of the notebook will be to read those results and make a figure that plots the global mean of the datasets over time. So the data that we want to use lives in the Earth Data Cloud. And the first thing we're going to run into is that you need to have an Earth Data login to access that data. It is free to create an Earth Data login, but we do need to remember to handle that. So the first step is going to be using the Earth Access library to pass those credentials and be able to query for that list of files. So that's going to return a list of file paths, but we aren't moving the files themselves. So we're also going to need a way for the Lambda function itself to authenticate so that when we pass it the path to the file, it can then access that data and read the data to do the calculation. NASA Earth Data lives in AWS in the US West 2 region. So to be able to access it, the notebook also needs to be running in AWS in the US West 2 region. So this is where you would use your own AWS account, set up an EC2 instance, which is a virtual machine, and run the Jupyter notebook from there. Some of our colleagues demonstrated how to set this up, a Jupyter notebook running in an EC2 instance last year in a similar Earth Data webinar. So we'll add the link to that recording and the tutorial that walks through how to do that. That's also linked at the end of these slides. Okay, so the notebook that invokes the Lambda function is also running in your AWS account. It's going to read the data from the Earth Data Cloud S3 buckets, do the global mean calculation, and write the results back to your own S3 results bucket, which can then be read by the Jupyter notebook to make that final time series figure. So setting this all up involves a little bit more than just configuring the Lambda function on its own. You need the code that you want the Lambda to run. The code can be packaged as a Docker container, or if it's small, you could use a zip file, or if it's really small, you could write it directly into the AWS console. A couple of the libraries that we're using in this example are a bit bigger, so we are using a Docker container. You will also need to set up the role for the Lambda to run as, so that you can give it permissions to do things like write to the S3 bucket. We are using the AWS parameter store to hold the Earth Data logging credentials so that Lambda can access them without needing to hard code them into the Docker container in a netrc file or even in the code itself. And then the Elastic container registry is where that Docker container gets deployed to, so that also is something that needs to be set up. And finally, we configure an S3 bucket to save the results. And that's the AWS infrastructure to support the Lambda service. You also need the Jupyter notebook that steps through the workflow, invokes the function and plots the results, and an EC2 instance to run that notebook in AWS. So what we are providing in this tutorial is in the blue box on the right. We have pretty extensive documentation that describes the workflow and how to set up all of these various components. We're also providing the Jupyter notebook that invokes the Lambda function and plots the results. And we have Terraform configuration files to make deploying the AWS services much easier. Terraform is a program that can set all of this up in your AWS account by you running a couple of commands. But in the documentation, we also go through how you would set up each of those services manually in the AWS console and what needs to be configured for each one so that you can understand sort of what it is that Terraform is setting up for you. We're also providing the Docker file that can be used to build the Docker container, and we describe how to build it and how to update it in case you want to make changes to the code that does that actual global mean calculation. Maybe you want to change it to do a different science calculation. You can play with that in the Docker file. And then all of this is going to live on the PO.DAAC cookbook. It's live up there right now. You can take a look, try it out, and let us know if you have feedback. The figure on the bottom is the results after running this for 1 year in 2022 on the Mir sea surface temperature datasets. And the red line is a higher resolution data set, and the blue line is a lower resolution. And it took about 30 seconds for these to run on 1 year of data. We haven't done a full benchmarking comparison yet, but anecdotally, one of our project scientists mentioned that doing this analysis offline on locally downloaded files for this specific data would take around 2 hours. So there are performance benefits to moving code and science workflows to the cloud. And we hope that this type of tutorial is helpful for people who are thinking about experimenting with some of those cloud services. We do have all of the resources that I mentioned linked from these slides and in the tutorial documentation. And now I will pass it over to Nikki, who's going to talk about some of the things we learned when moving one of our on-premise data workflows that we use operationally at PO.DAAC into the cloud.
Thanks, Victoria. All right. My name is Nikki. I'm a cloud adoption engineer with PO.DAAC, and I'd like to talk about transitioning code to the cloud. More specifically, I'd like to speak about PO.DAAC's experience with transitioning science data processing workflows to the cloud as a more advanced use case for working within the cloud. So to set some context, I think you can view Julie's demonstration as a way to break into using data in the cloud, and Victoria's Lambda SST workflow as a way to begin computing that or processing that data in the cloud. And then this use case can serve as guidance for transitioning your code and science workflows into the cloud. AWS has a large ecosystem of services that can be confusing to new users, scientists, and data providers. As part of our own transition, we have assessed the landscape of those services and done some of that homework to find services that may be quite common to the NASA ecosystem and across our user communities. So PO.DAAC, as mentioned, has migrated its data from on-premise storage to the cloud, but we were still running a few data processing workflows on-premise, which does not really align with the new cloud paradigm we see for data access and use. So we identified a key science data processing workflow that needed to be transitioned to the cloud, and another workflow that isn't quite cloud ready but needed to be modified so that it retrieves input data from the cloud. So the objectives around that work was first to migrate the on-premise workflow named Generate to the cloud so that we can take advantage of compute power and scalability while also processing data in the same region as it is stored. Generate is a PO.DAAC science data processing service that creates Modus Aqua, Modus Terra, and VIIRS level 2P sea surface temperature products for the Group for High Resolution Sea Surface Temperature project. This particular transition of code to the cloud can serve as a template for future workflows. We can also use this experience to assist our user community in similar endeavors and help navigate that variety of AWS services. We also wanted to point the on-premise workflow we call MUIR to cloud-based endpoints for the level 2P datasets the workflow uses as input. MUIR stands for Multi-Scale Ultra-High Resolution Sea Surface Temperature Analysis. It's another PO.DAAC science data processing service that produces level 4 sea surface temperature products. It is one of PO.DAAC's most popular datasets and was funded by the NASA Measures program, which stands for Making Earth System Data Records for Use in Research Environments. It's the default view in SODA, which is State of the Ocean. It's a visualization tool, and it's used in the Earth Information Center exhibit installed at NASA headquarters. So all of this work helps us to support the access and use of data in the cloud as our user community adapts to the new possibilities provided by cloud-based storage. So let's take a look at an overview of both workflows and talk about the data pipeline between workflows as they are connected. So the data pipeline starts with the Ocean Biology Processing Group, which produces level 2 datasets for Modus Aqua, Modus Terra, and VIIRS. The Generate workflow downloads the level 2 sea surface temperature data from the Ocean Biology Processing Group, or OBPG, and reformats that level 2 data to level 2P granules so that they conform to the Group for High Resolution Sea Surface Temperature, or GRIST, file specifications. The granules are then ingested into PO.DAAC and made available to the user community in the cloud. So in the diagram listed below Generate are some of the AWS services we use to translate the on-premise workflow to the AWS cloud. And so once the Generate workflow runs, it produces the level 2P granules, and they're stored in an S3 bucket. At that point, MUIR, the multi-scale ultra-high resolution workflow, can use those level 2P granules alongside several other input data to produce the high-resolution level 4 global sea surface temperature datasets, which are also stored in the cloud. The data from these datasets, the level 2P datasets, needs to be available for the daily execution of MUIR, so we use another tool developed by PO.DAAC, the data subscriber, which is the twin of the data downloader, but it allows us to subscribe to the level 2P datasets and download granules as they become available. So why should we transition to the cloud? And I think we can generalize this to a lot of different workflows that might want to be transitioned or could benefit from that transition to the cloud. I think as we see more and more missions delivering larger and larger volumes of data, it becomes harder to download and process that data locally. So a great kind of thing to look at is what scale you're operating on and how can you, at what point can you no longer download and store that data? So for Generate, it does operate on a global scale, and transitioning it to the cloud provided us many benefits. Some of them include allowing us to decrease our execution times, scaling up and down with the volume of input data as it becomes available. We can gain insights into our workflow through the central location of logs and metrics. We benefit from centralized security practices. And through this process, we've created a modular workflow that allows for flexibility and modifications, allowing us to make future improvements to the workflow and the data sets produced by the workflow so we can ensure future availability. So what was the process that we developed and followed to first transition the Generate workflow to the cloud, as well as point the Mirror workflow at cloud-based endpoints? Both followed similar paths, and I'll try to indicate which step applies to which workflow when applicable. So for the first step, it applies to both workflows. We mapped out each workflow to understand the flow of data or the data pipeline. So we needed to understand the inputs that are required and how they're processed in the workflow, when and where that input data becomes available. We also had to understand how intermediate data is stored and used throughout the workflow, so how stages in the workflow might communicate with each other. And then we also needed to understand how output is created, formatted, and stored. We found diagrams to be really useful in visualizing the flow of data, so that we could all be on the same page about what the workflow is accomplishing. And it also helped us to define a list of requirements, which is step 2 and applies to both workflows. So the requirements are what the workflow should do or accomplish alongside any limitations. A few examples of these for Generate is it needed to run hourly on 3 different data sets in parallel. We had to work around or work with IDL licensing, as 2 of the components in the Generate workflow were written in IDL, which is a programming language. And we also had to understand when and where the ocean biology processing group data was made available. For Mirror, our requirements centered around ensuring the level 2P data was available for the daily execution of the workflow. So then in step 3, we broke both workflows into components, modules, or stages. And then for Generate only, we containerized those components. So a container serves as a way to isolate the environment that the code for each component needs to be able to run. For Generate, this is really useful because a lot of the components are written in more than one programming language. So we were able to wrap those dependencies for each component into a single executable package. So kind of one container per component. This also allowed us to easily transition the execution of those containers to the cloud, as many AWS services support the execution of a container. From here, this meant understanding the input stage or input operations and how they impacted the heavy lifting or data processing operations, so we could understand when data needed to be made available. So the next step is for Generate only. We reviewed the landscape of AWS services in order to match those services to the requirements of each component and the entire workflow. So we looked at the data flow and requirements list that we created in step 1 and step 2. We reviewed a lot of AWS documentation and tried to understand the pros and cons of implementing a solution with various services. We developed 3 different solutions, and we picked one that matched the execution requirements of the workflow and the flow of the data through that execution. We also needed to accommodate expected CPU, memory, and storage usage. So not to delve too deeply into AWS speak, but for the Generate workflow, for the data processing side of things, we went with the AWS Batch Service and AWS Lambda. For data storage, we chose the Amazon Elastic File System for intermediate data and the Amazon Simple Storage Service for our final L2P granules. And then sort of baked into all of this is CloudWatch, which provides logging and metrics. So we were able to gain some insight into the Generate workflow. Step 5 applies to mirror only. We needed to strategize how to set up the PO.DAAC data subscriber so that the level 2P input data sets were available for daily execution. We decided to execute these downloads on an hourly basis for each data set, making as much data available as possible for the execution and mirroring what was available when data was stored on premise. In step 6, we implemented and deployed the solutions we defined in step 4 and 5. So for Generate, we use Terraform, which Victoria mentioned is an infrastructure as code tool to deploy our components and help us keep track of how we configured the AWS services. For Mirror, we copied the code base to a development environment, so we're not impacting the operations environment. We created a GitHub repository to track code changes, and then we strategized the best way to deploy those code changes to the operations environment using the development environment as a test bed. So speaking of testing, we tested the solutions. For Generate, we ran a stress test in AWS on a full month of data to mimic the largest volume of data we might ever attempt to process. And then we compared the results produced in the cloud to those produced on premise. And for Mirror, we compared the granules produced in the development environment to those produced by the operational environment. So going through that process, we did encounter challenges and some lessons learned. I think this can be a nice checklist for what to think about when approaching a transition of a local code base to the cloud. So the first is around requirements. It's helpful to define a core set of requirements and stick to them. We found it really easy to want to continually add the need for new functionality or to try to squeeze in one last modification, but it was really important for us to complete this transition. So we defined what was absolutely necessary to execute and create the final output. And we kept a backlog or a list of all future changes that we had defined earlier and sort of the nice to have features that we would like to implement. We prioritized these items and gave them a time estimate so we could start to strategize the future of the Generate workflow. The next challenge and lesson learned is around error detection and recovery. This is thinking about what actions you want to take when your workflow runs into an error. So how do you know when, where, and why something went wrong so you can fix it? It's also important to think about how to pick up where your workflow left off after an error was encountered and interrupted that execution. So for the Generate workflow, one of the components that kicks off all of the processing tracks state in a text file. So this is just tracking what files it's downloaded and processed previously. And every time it runs, it checks that text file. So just really simple way to pick up where we left off. And so along those lines, we also have to figure out how to recover from errors. So we're running into the same type of error pretty consistently. So we developed a component that detected that specific error and resubmitted the input data to the workflow for processing. We also have a manual way to resubmit data to the workflow so we can recover as quickly as possible when we encounter an error. The next, somewhat related, is workflow insight and monitorability. How do you know what your workflow is currently doing and track what has happened? I think it's helpful to start off with logging and make sure to include print statements that are clear, concise, and consistent in your code. All of the logs are stored centrally, and you can search on them across time. So if you have a couple of keywords that you find helpful to search on that are important to your workflow, you can build those into your component print statements and search on those so you gain some insight into what's going on in your workflow. You can certainly get more complicated from there. For example, for Generate, we created a dashboard that pulls data from the logs so we could see the number of granules produced per hour and daily. And finally, how do you know if your transition went successfully? You need to define how you measure success. For Generate and Mirror, our measurement relied heavily on the comparisons to the on-premise workflow. So for Generate, we compared the data produced by the cloud and the on-premise workflow to make sure the data was exactly the same. We wanted our transition from on-premise to the cloud to be transparent. We did not want to impact the granules in any way. So we also looked at execution times to make sure we were meeting the user community's expectations around when granules are made available. And then in the bottom half of the slide, these are visualizations that relate to the process or the measurements of success we developed for Mirror. So We first compare the development version of Mirror to the operational version, and that's the first visualization, and that's an early one. So there were some differences that weren't satisfactory. So we then compared the development version and the operational version of the data to a completely different data set, and that's the second visualization. And from there, we developed a process for these comparisons so that we could narrow down any issues or bugs, figure out where the input data might be impacted, and resolve them. And then we can recompare iteratively until we found there were very few, if any, differences, which is represented by the third visualization. So transitioning code to the cloud is no small task. It's helpful to develop reliable checks to ensure workflows in the cloud are consistent with previous results produced by on-premise workflows. But through our experience with these transitions, we found we were able to gain the more traditional benefits of moving into the cloud, but also some additional ones. We were able to improve our on-premise workflows by revisiting the code and functionality of each component. So we're able to improve our ability to modify components in the entire workflow, provide better insight into what each workflow is producing, and update some of the components so they function more reliably. So it was actually a really beneficial process for us to go through, and we ended up with an improved workflows in both pieces. Here is a list of resources. On the left is all of the data sets that I mentioned, and on the right is any technical terminology or technology that I mentioned in case you would like to look into those further. I want to thank you for joining us. We're really happy to share 3 use cases with you, which demonstrate how the different levels of users may approach working with and processing data in the cloud. We hope that we've given you some ideas and guidance on what working in the cloud may look like for you. And with that, I'll hand things back to Jennifer.
Okay, thank you so much, Nikki, and thanks to all of our speakers. At this point, we will log off from the audio component and leave the virtual meeting space open. I'd like to thank all of you for joining us today, and you should expect to see the recording as well as a link to the presentation in the next couple of days. All right, thanks so much, everybody. Goodbye now.